looks like there's a lot of people missing, but there's really only 11.
I think they're still
Only
eating
11
turkeys.
missing?
Yeah.
Oh,
So
yeah.
far.
11. That's a lot.
That's okay. Well, I think people,
We don't need them.
yeah,
No, we don't.
people are kind of like, they're remembering, oh yeah, I had all this stuff to do, and stuff that was due. So I'm just gonna skip class and get all the stuff that I had to do today, that I should have been doing over break. That's usually what Monday after break is for, which is why I don't assign anything. We shall see.
Is game theory a part of discrete math?
It can be.
It can be.
Yes, absolutely. Unfortunately, we need a little bit more stuff to do that. Like
Really?
for specifically game theory, you have to go through win-loss analysis, and that usually takes about a couple of weeks just to teach that theory. So it really is discrete when it comes down to it. So yeah, it can be. In fact, it is. Okay guys, so just a heads up as to what's going to go on. Today we're going to finish up the last two recursion problems, and then we're going to go ahead and start our last topic in the course, which is going to be graph theory. And then hopefully Wednesday we'll be able to finish up our graph theory stuff. Okay. Next Monday, what we're going to do is we're going to use that day to review for the final examination. Okay. And then what I'll do is I'll make assignment number 12, the last assignment, due next Wednesday as well. Assignment 11, which is what we're going to finish up today, that'll be due next time. Okay. If for some reason we get all the review stuff done on the 5th, then what you guys can do is you can just email me a copy of the assignment 12, and I'll just grade it that way, so you don't have to physically give me a copy. Our final is scheduled for the 14th, and because it's a 3:15 class, it goes from 3:15 to 5:15 in this room. Okay? All right, so that's what's going on. Posted on Blackboard if you guys have any questions. All right, so any questions about anything, guys, before we get started? Okay. So a long time ago, we started this thing called recursion, and I wanted to finish up the recursion today. So one of the things that we learned how to do last time was we took something that was recursive and we wrote it in a linear form. Well, not linear necessarily, but we wrote it into like an indexable form, so that way you could just substitute a number directly and get to the answer. Okay, so that's what we're going to look at today to finish those up. The ones that we've looked at so far weren't so difficult. Okay, so we're going to look at more difficult ones today. So I want you guys to take a look at this recurrence relation that we have up here. So we have d sub k equals 4d sub k minus 1 plus 2. The initial value is 3, and k always has to be bigger than or equal to 1. Okay. You may or may not remember, but the way that we tried to be able to write something like this into a non-recursive form was we used the method of iteration. Okay? So we started by writing the first, the second, the third instance, and hopefully we saw a pattern. Okay? So let's go ahead and do that. Okay? Now d sub 0 is clearly equal to 3. D sub 1, all we're going to do is take the previous instance, plug it back in for d sub k minus 1, and then we have the 2 on there. So d sub 1 is going to be 4, quantity 3, plus 2. Right. Now we all know that equals 14, okay? But 14 doesn't necessarily help us out. Okay, in fact, I know it doesn't in this instance, okay? It might, you guys might think it does, but it doesn't. Okay? D sub 2. Okay. Now, if we think of it in the way that a computer would think of recursion, that might be the easiest way to start this, okay? So, D sub 2 is going to be 4 times the previous instance. The previous instance was 4 times 3 plus 2. And then we have another plus 2 as a result of this plus 2 that's out there, okay? So, does everybody see what we're doing here? All we're doing is we're just plugging the previous instance back in whenever we see a d sub k minus 1, okay? So this guy right here, that's substituted in there. All right. Now, a lot of us would look at that, we'd go through, we tried to simplify it, okay? And that's exactly what we're going to do, but the question is, how far do we simplify it, okay? So let me show you guys maybe 3 or 4 or 5 different ways that we can simplify this, okay? One way we can simplify it is just do 4 times 14 to get 56. 56 plus 2 is 58, okay? So one way we could write that as 58. Another way we could do this is write this as 4 times 14 plus 2, okay? Another way that we could write this is we could write this as 4 times 12 plus 4 times 2 plus 2, okay? Another way that we could write this, okay? All I'm doing is I'm just showing you guys different ways to write this, okay? Another way I could write this is 4 times 4, or 4 squared, times 3, plus 4 times 2, plus 2. Another way that I could write this, if I really wanted to, is I could just write this as 4 times, I guess I could just write this as 4 times 12 would be 48, plus 8, plus 2. Okay? So the question is, which of those ways is the best way to write this? Okay, there's 5 different ways, okay? And unfortunately, one of the things that we learn in recursion is that it's difficult to maybe pick the best right way. So let me ask you guys, which one do you think is maybe one of the best ways that we could write this?
4 squared 3 plus 4 times 2 plus 2, that way?
This guy? How come?
Because if you do this, then you can find that index, that square is like with the index, you can find a relation with that if you do 2 more.
Maybe we might be able to find like a relationship between the index and maybe the exponent. Okay, that might work. Okay. Also, if we could try to write it in exponent form, it might be helpful for us. So I don't think 58 is going to help us too much, because who of us can see a pattern of 3, 14, 58, and then the next one after that? That's not going to be helpful. Okay. So I think out of all 5 of these, I think this one's going to be the most useful for us. Okay? If you don't believe me, just try some of the other ones. Okay? You might be convinced otherwise. Let's find d sub 3. So all we're going to do with d sub 3 is we're going to take the previous instance and we're going to substitute it back in to d sub k minus 1. So it's going to be 4 quantity, 4 squared times 3, plus 4 times 2, plus 2, plus 2. Okay. And just like we did in the previous, let's just distribute the 4, but keep it in the exponential form as opposed to computing. Okay, so this is going to be equal to 4 to the 3rd times 3 plus 4 squared times 2 plus 4 times 2 plus 2. Okay. All right. And again, one of the most difficult things about recursion is just being able to see the patterns that are going on. Okay? And like I said, these are just 5 of a number of ways that we could have written that. Okay? I mean, if I wanted to, I could probably have written it in like 30 ways if I wanted to, but I'm trying to show you guys the most efficient way. Okay? Let's just do 2 more iterations or 2 more instances, because then we might be able to see a pattern that's going on like this. Okay? So I'll just go over here. I'm going to write d sub 4. So d sub 4 is going to be equal to 4 times that instance. So 4 times the quantity of 4 cubed times 3 plus 4 squared times 2 plus 4 times 2 plus 2 and then another plus 2, And notice each time, guys, there's another +2 because of the +2 in the original recursive sequence, okay? If I distribute, we wind up with 4 to the 4th times 3 plus 4 to the 3rd times 2 plus 4 squared times 2 plus 4 times 2 plus 2. And now maybe you guys are starting to see a pattern. Okay? In fact, one of the things that we notice is that there's descending order of exponents of power 4. Most of them have a coefficient of 2 along with it. Now there's this one oddball one with the 3 in it. Okay? If I was to ask you guys to make a guess about d sub 5, okay? Does somebody think they might know what the 5th instance looks like? So, James, go ahead.
4 to the 5th times 3,
Okay.
plus 4 to the 4th times 2,
Uh-huh.
plus 4 to the cube times 2,
Uh-huh.
plus 4 squared times 2,
Uh-huh.
plus 4 times 2, plus 2.
Sounds good to me. All right. So, let's hold on to that for a second, okay? Because we have, remember, the whole goal is to figure out what the nth iteration would look like. Okay, hopefully it wouldn't be recursive, okay, which it isn't for me. All right. Now, let me ask you guys this question. If I was to say, because remember, the whole goal is to figure out what maybe the nth iteration would look like that's not recursive. Okay? So if I was to ask you guys what the nth iteration, and obviously we have a first, second, third, fourth, and fifth, okay, does somebody think they might know what the nth iteration would
4
look like?
to the power n
Okay, so
times
4 to the n, go ahead.
3 times 3
Okay.
plus 4 to the power n minus 1
Uh-huh.
times, what is it, n
Two.
minus 2, yeah,
Okay.
plus 4 to the n minus 2
Uh-huh.
times 2
Okay.
plus 4 to the power n minus 1, 3, yeah, plus 2 times 2,
And that would just keep going on, right?
yep.
For how long? Forever until,
Plus 4 to the 1 times 2, plus
yeah, so 4 squared times 2
2.
plus 4 times 2 plus 2.
2.
Okay, nice. Okay, I just wanted to write the last 3 of them. Okay, well that looks good. I mean, hey, at least it's not recursive. All right. Now the problem is that we're asked to write this into the closed form. Okay? Remember last time I gave you guys that worksheet with the special summations on it? Okay? Let's take a look at that. Because maybe there's something in there that might help us, hopefully. If it doesn't, then I might as well just quit this problem. Okay. Alright. And let's look maybe towards the bottom of that page. Okay. Do you guys see any formulas that might be helpful to be able to write something like
4
that?
to the power n minus plus 1,
Yeah, this guy, like maybe right here. Oh, yeah, so you got packages to paper. Okay. Guys, doesn't this look like it might be helpful? Because don't we have like a 4 to the n and a 4 to the n minus 1 and a 4 to the n minus 2? So I think that might be really helpful to us after we doctor it up just a little bit. Okay? So what's one thing that we might do to be able to use this formula that might be maybe not so obvious, but we could do? I see a 2, 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 I see a 2. Can I factor a 2 out? So let's write it like this, maybe. 4 to the n times 3